Hi guys. Today we're going to try to know how to get the quantum numbers from the elements. These are the fingerprints for the elements because each element has different quantum numbers. They were proposed by Schrödinger, and it's kind of a mathematical explanation to what's going on with the differential electron. The differential electron is the last one standing for the electron configuration. As a reminder, the orbital types that we have here can hold up to different number of electrons. So S can hold up to 2, P can hold up to 6, D can hold up to 10, and F can hold up to 14. The different lines that you see here are the suborbitals that you can find for each type of orbital. Okay, so let's start checking the quantum numbers. The first one is represented by the letter N, and it's the principal quantum number. This indicates the level of energy given by the last electron standing. So in this case, N for my differential electron would be 3. This is also associated to the period in which you find the element in the periodic table. Okay, so here you go. This number here, this 3 from the condensed electron configuration, is indicating N, or the principal quantum number. Now, in the case of L, which stands for angular momentum, it describes the type of orbital. So I mathematically assign a number based on the type of orbital that I have. If I have S, L will be 0. If I have P, L would be equal to 1. If I have D, L is 2. And if I have F, it would be equal to 3. Okay, in this case, since I know from my electron configuration that my last electron is found in P, then L would be equal to 1. M has to do with the magnetic quantum number, and this indicates the orbital orientation, meaning the suborbital where I'm standing. So in this case, what I'm gonna do is I take P, and I know that P has 3 suborbitals. So this, mathematically speaking, I start from the middle, it would be 0, and then I go from minus L, that it would be minus 1 because we said that L was 1, standing from 0, and then to 1. So this would be minus L, 0, plus L. Okay, now if I do my electron configuration, I have 1, 2, 3, 4, 5 electrons. This is given by the last information here. Okay, so I take where my last electron was positioned, just because in this case my quantum numbers are associated to the differential electron. But I can actually calculate the quantum number for every single electron that chlorine has. So in this case, M would be 0 because my electron was positioned in 0. Okay, now for S, which is the spin, I have 2 possibilities. This describes to which side my electron is spinning. So I represent it by plus 1/2 or minus 1/2. If my S is positive, it means that my electron is heading up. If my S is negative, it means that my electron is heading down. In this case, if you pay attention, my electron is heading down. So S would be equal to minus 1/2. So there we go. We have the 4 quantum numbers to represent the differential electron for chlorine. This would be N equals 3, given that it is on the 3rd period or position on the 3rd energetical level. L, which equals to 1 because my orbital is P. M, equals to 0 because it is positioned on the middle suborbital, and S would be minus 1/2 because my differential electron is looking down. There we go. This can be calculated, as I told you before, for any electron that you want to describe. It doesn't have to be specifically the differential electron, but we do it with the differential electron because that's what basically differs from element to element. There you go. So one trick here. Now imagine that I tell you that my differential electron for one given element is 2s1. How can I take that information to know what element I'm talking about? So we said that this 2 represents N, which is my principal level, and that was associated to the period. So then I know that the element I'm looking for is here. Now I also know that this S here represents L, which is the orbital type. I also know that S can only hold up to 2 electrons. So this limits my space to this part here of the periodic table. This would be S. This here would be P. This in the middle would be equivalent to D. And here we've got F. This matches with the number of electrons that we could hold in each type of orbital. In S, we can hold up to 2. In P, we can hold up to 6. In D, we can hold up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And in F, we can hold up to 14. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, you see 15 here because don't forget that the lanthanide and the actinide series come from here because they couldn't be placed all together in the periodic table. Okay, but lanthanum and actinum actually belong to D here. The rest are the ones that belong to F. So, given this, I know that I have only one electron in S, so the element I was looking for is lithium, okay? From this, I can also calculate, as we did before, the quantum numbers. So N would be 2, given the energy level and the period. L, based on the type of orbital, would be 0 because it's S. M would also be 0 because in the case of S, since I only have one type of suborbital, I don't have any other possibility, okay? And then S related to the spin, since I only have one electron, this should be heating up, right? So it would be plus 1/2. So that's another way to use the information from the quantum numbers and associate it to the periodic table, okay? So given the differential electron, since we said that quantum numbers were like the fingerprints, I can actually determine what element we're talking about. Cool, huh?